Hello everyone, welcome to this video on multiple linear regression. Here I'm going to look at one example related to an engineering experiment. It's called wire bonding experiment. An experiment was carried out to study the effect of four process variables on ball bond shear strength. The response variable is Y equal to ball bond shear strength. The explanatory variables are x1 is equal to force, x2 is equal to power, x3 is equal to temperature, and x4 is equal to time. This experiment has been carried out at some specific values of x1, x2, x3, and x4. And we have the data like this. So you can see that force, some specific values, 30, 40, 30, 40, 30, 40, those, and then also 25, 45, and so on. The power and temperature are also, everything is controlled here, right? Time is also measured at specific times, specific values. So all the x variables are controlled variables, right? Only y is actually a random. That is the strength. Only y is a random variable, right? So the question is, how do force, power, temperature, and time affect ball bond shear strength, right? So the main idea is, main objective is to find out the effect of each variables. How do they affect? So one way to answer this question is to build up a model connecting the shear strength y and uh, the other x variables. By that way, first we will be able to identify the important variables, or sometimes called significant variables, significant x variables for modeling y. And then once you have a good model, then from the coefficients of the selected x variables will uh, give us an idea about the effect of each of those variables. So we have this data. I have actually uh, put them into a CSV file, right? So I have read here those that data set, and then uh, first thing to look at do is actually when you're analyzing this kind of, this is a multivariate analysis situation. Here, uh, first thing to look at is uh, what kind of relationships are existing between each pair of observations in the analysis. But of course, in this case, we are going to look at only the relationship between y and x1, y and x2, y and x3, and y and x4 separately. Those are the only relationships that I will explore, because the other things will not be important in this case, because x1, x2, x3, x4 are controlled variables. They are in at some control levels, and therefore there's no point of looking at the relationship between x1 and x2, x1 and x3, x1 and x4, and x2 and x3, and so on. In a general, uh, for example, if you have collected data from an observational study, usually looking at the relationships between x variables will also be useful. But in this case, it's not going to be very useful. Therefore, I'm going to look at only the relationships, possible relationships, or explore what kind of relationships are existing between y and each x variable. So I asked to plot. I have uh, given a short name for this thing, wire bonding data. I denoted by WBD. So I take the plot of force. This is the x value, the x variable, and then strength is the y variable. And then I plot strength versus power, strength versus temperature, strength versus time. So these are the graphs that I got, scatter plots. Right. So when I look at the strength versus force, I don't see any particular pattern here. Right. So even if there is actually a pattern, it's not very clear from this data, but there might be a relationship which we will be able to capture through the model. That is possible, right? Because here the relationships are not only bivariate, there can be some relationships with with the x variables itself. So therefore, when we just plot the y versus some x, we might not see any relationship, but still there might be some relationship with that variable when we model them, right? So therefore, you have to be careful about that. Don't just throw away that variable force just because there is no apparent relationship in the scatter plot, right? But what is important is if there seems to be a relationship, then it's important to observe what kind of relationship is important, evident here, appears to be there. Right. So, for example, if you look at the relationship between strength and power, you can see that there is an increasing relationship. When the power increases, the strength tends to increase. So, at the first step, we might think that the relationship is a straight line relationship. And then when you look at the strength versus temperature, again, there's no very clear relationship in the scatter plot, but one might think that there is a very weak positive relationship, right? There's some very weak evidence of a positive relationship, so we'll keep that in mind. And if we look at the relationship between strength versus time, again, there is no pattern here. So even if there is a relationship, it's not apparent from the scatter plot, right? So mainly, if there is any relationship, according to the scatter plots, power and temperature will be important. The other may or may not be important in modeling in the strength, right? So anyway, we will, because there are only four variables, it's not a very big model. So we will first consider a multiple linear regression model, including those four variables first, right? So therefore, we'll consider yi, that is the ith observation, right? Coming from the ith experiment, is equal to beta naught plus beta 1 x1 right? That is the power used in the ith experiment, beta 2 x2 that is the level of x variable x2 in the ith experiment, and beta 3 x3 plus beta 4 x4 plus an error term. So this is the model for the ith experiment, where I can go from 1 to 30. There have been 30 experiments, right? So that is the model that we will consider. So now I'm going to fit the model using R. So this is the command that we use. So first of all, I get the data by reading the CSV file, read.csv. And then we use the R command called LM, linear modeling, right? So I fit the model and put the output into wire bonding model. That is the name that I give for the output. So it's LM strength. Strength is the Y variable, and then this is the tilde mark, right? Tilde. And then we include the variables that you want to include. Power plus force plus power plus temperature plus time, right? So by this command, actually what we mean is this model. This is the model that we mean by this command here. And the data for this model is coming from this data set here that we have already read into the computer via bonding data. So that is the command that we use. And then I got the data, I got the output, and then I look at the summary of that output. So that is the name of the output that I have used here. So I look at the summary just to get some idea, right? As an initial idea about the model, right? So these are not that important at this point. What I am interested in is actually these values here, right? These are the fitted coefficients for so beta 1, beta 2, beta 3, beta 4, right? Coefficient, estimated coefficients. And what I am interested in at this point is actually these p values. These are called p values, right? Remember, we are testing in this case. Let me write down. To remember, we are testing using these t-tests about individual coefficients, right? For example, one hypothesis like H naught, say beta naught is equal to 0 versus H1 beta naught not equal to 0. Another hypothesis. So this is here we are testing that hypothesis, and this is the p-value corresponding to that t-test. And then we are interested in testing whether beta 1 is equal to 0 versus H1 beta 1 is not equal to 0. And that this is the output corresponding, or the p-value corresponding to that t-test. And similarly here I'm testing whether beta 2 is equal to 0 or not. Here I'm testing whether beta 3 is equal to 0 or not, right? So you can see that how do we decide in this case how to make the decision? If you remember the p-value method, reject H naught if the p-value is less than, usually we take 0.05 as the level of significance. Right? That is the usual level that people use. But if you want, you can use some other small value according to your interest. Right. But here we will be using 0.05 as that is the generally used value. So you can see this p-value here, the first one, is less than 0.05. Therefore, we say that beta naught is not equal to 0. Right? So we reject H naught. That means we decide that beta naught is not equal to 0. But this one is greater than 0.05. Therefore, we do not reject H naught in that case. So therefore, there we decide that beta 1 is equal to 0. Right? That is the null hypothesis. We accept the null hypothesis in that case. We don't reject. This p-value here is much smaller than 0.05. Right? So this is smaller the p-value, it can be considered as we having more evidence against the null hypothesis. So here we have very strong evidence against the null hypothesis. Here we decide that beta 2 is not equal to 0. We reject H naught. Right? And also from this one we can decide that beta 3 is not equal to 0, because this is much smaller than 0.05. From this one, we decide that beta 4 is equal to 0. Right? So remember, beta 1 is the coefficient for force. Right? Beta 4 is the coefficient for time. Right? So according to this initial or the preliminary analysis, it seems that force and time are not that important in predicting the shear strength. Right. Let's look at further here. It says R squared value is 0.71. Adjusted R square value is 0.668. Right. So both are roughly the same, 0.7. So what does it mean? R squared value gives you an idea about the goodness of the fit. Right. It tells you here, out of all the variation in Y, about 71% of the variation is explained by this model, right? This particular model, right? So that's a large proportion. But anyway, this is not the model that we are going to settle with. So using this information, I will now consider a reduced model. I will remove this one. I will remove this one, this variable and this variable from the model, and then refit the model with only these two and see whether there is a very large difference in R square, for example, right? Uh, if that is the case, then we should not remove like that. But otherwise, if there's only a very small reduction, right? When you remove some variables, R square will be reduced a little bit. But if the reduction is not that large, that reduced model can be considered as a better model. Remember, we talked about the parsimony principle and so on. What we want is a simpler model uh, with a reasonable percentage of variation explained by the model. Right. So we will now do that. Remember, at this point, I am assuming that the model assumptions are reasonable. Otherwise, I cannot actually interpret any of these p-values, right? If the model assumptions are not reasonable, any of these p-values will not be meaningful. Right? But at this preliminary level, I'm assuming that model assumptions are okay. And actually, I will do is once I come to a reasonable, acceptable model, at that situation, I will be checking whether the model assumptions are reasonable, right? Using residual analysis, right? But otherwise, it's not usually possible or it's not usually done that residual analysis is done at each fit. For example, you might start with a larger model and then consider a reduced model, and then even further, you may using some information in the output, you will be probably improving the model. And we are not going to do the residual analysis for each of those models. Usually, when we come to a reasonable model, at that point, we will be checking whether the model assumptions are reasonable for that particular model, because this is not the model that I'm going to consider. So at this point, I'm assuming that these p-values are meaningful, at least approximately. They will be giving you rough, correct ideas. Okay, according to the output, force and time are not significant. Therefore, a reasonable reduced model keeps only power and temperature. So now I am fitting the reduced model, and I am putting the output in wire bonding reduced model. Still, I am using the LM function, LM command. Strength is still the Y variable. Now only power and temperature are in the model, right? So here I'm going to get the model summary again. Right. So you can see the model summary. Now all the variables, the coefficients corresponding to these variables are significant, right? So it says beta naught. In this case, in the model is not significant. Is significant. And this coefficient corresponding to power is very, very significant. And the coefficient corresponding to temperature, coming with temperature in the model, is also significant. All three coefficients are significant. So usually people say the variables are significant in that case. When you say variables are significant, what we really mean is the coefficient attached to that is statistically significant. That's what it means. But let's look at now the difference in R square. Earlier, R square value was Point, okay, we will look at because now we are comparing R square with two models with different number of variables. Here in this model, there are four variables. In the other one, only uh, two variables, right? Of course, beta node, there are three coefficients. But anyway, in this case, it's better to compare adjusted R square. Adjusted R square is have been calculated by adjusting for the number of variables. So here, adjusted R square is 0.67 approximately. What is the adjusted R square here? It's again 0.66. So there's no much difference even in the R square, adjusted R square, even if we drop two variables. So that gives you an idea about those two variables are actually not important in modeling the shear strength. Right. So therefore, we will consider this as a reasonable model if now, for example, the model assumptions are reasonable, because here also I am looking at the p-values. These p-values will be meaningful only if the model assumptions are reasonable. Right. The residual standard error is 5.21. Residual standard error is this one. Actually, residual standard error has to be a smaller value compared to the degree of freedom. Right. In this case, residual standard error is much, much smaller than the degree of freedom. So that's a good idea, good indication too. But the more important thing is R square and adjusted R square. Right. R square is 0.685, that indicates approximately 68.5 of the variation in strength is explained by power and temperature. The adjusted coefficient of determination R square adjusted is also very close to that, reasonably close to R square. This suggests that the explanatory ability of the model is not substantially reduced after counting for the number of explanatory variables. Right. So therefore, this model and the full model that we considered earlier uh, explains approximately the same amount of variation in Y. Right. In addition to that, of course, overall F test indicates that all the variables in the model are not any of those not all of them are equal to zero. So actually that's not an important one, because once you have identified that individual parameters are significant, this F test is not meaningful anymore, and not useful, right? It's meaningful, of course, but not very useful in this situation. However, conclusions based on the F test and the individual T test that we made here are reliable only when the underlying regression model assumptions are reasonably satisfied. Therefore, the validity of these assumptions must be examined before drawing final conclusions from the fitted model. So this is a part that many researchers don't actually do, or even though they do it, they don't report it in the research paper, right? So therefore, deciding whether a given output and given conclusions in a research paper are valid or not is very difficult, right? Most of the conclusions in research papers where the conclusions were made based on, say, regression modeling may not be valid actually, or we may not be able to say whether they are valid unless they say something about residual analysis, right? So you have to at least say you carried out the residual analysis and found all the model assumptions to be reasonable or valid in this situation. You have to mention that. Otherwise, uh, the results are quite questionable, right? So that is an important thing, remember, right? So therefore, I carry out the residual analysis, right? Remember, residuals are considered as uh, uh, representative values for the errors in the model. Errors, right? Residuals and errors are not the same. Residuals are y minus y hat, right? Observed value minus the fitted value. That is what the residual is. But we expect the residuals to behave similar to the errors. So therefore, There are model assumptions. Using model assumptions are usually on the errors, right? For example, we assume that the errors are normally distributed, errors are independent, errors are homoscedastic, and so on. I explained those things in the previous video, right? So assumptions are about the errors in the model, right? Remember again, this word error doesn't mean mistakes, right? That is just a technical word used in the model. That is the difference between observed y and the considered model value, right? The value on population fitted value, right? But because we cannot really observe errors, we cannot check whether the model assumptions regarding the errors are valid or not, because we are not able to get errors, right? Instead, what we have are residuals, right? So instead of checking whether the model assumptions regarding errors are valid or not, what we usually do is we check whether the residuals uh, behave as we expected, right? If the errors have the model assumptions, if the errors satisfy the model assumptions, then theoretically there are certain things that residuals should have, right? Residuals should have as properties. So what we do is we check whether those properties are satisfied by the residuals. So I get the fitted values because we usually want to plot the residuals. Right? There are several types of residuals people consider: row residuals, and standardized residuals, and studentized residuals. So I have obtained all those residuals here. First of all, fitted values I can obtain using the command fitted, and then within bracket the output name of the model. And the residuals I can get with the command residuals. And standardized residuals I can obtain with the using the command r standard, and then within bracket the output name of the output of the regression model. Studentized residuals can be obtained using the command r student. Right. So these are the commands that we use, or codes we use to get the fitted values, residuals, standardized residuals, and studentized residuals. Actually, the best residuals to look at is the studentized residuals. But standardized residuals and studentized residuals are, in most of the cases, they are roughly the same. There's some difference. Uh, uh, so therefore, in most of the cases, people look at standardized residuals. Right? One reason may be that some people even don't know what the studentized residuals are, what is the difference between standardized and studentized residuals. Right. So therefore, I also have used standardized residuals, but otherwise, you may be confused if you look at some outputs, some other research papers, and I am looking at here the studentized residuals, and they have looked at standardized residuals. Right. But as I mentioned, the best residuals to look at is studentized residuals. And then there are certain things called leverage values. Leverage values are obtained using this hat values command. These hat values are actually, I will just mention this is not important, I think probably for you, but I will anyway mention this. We can show that y hat values, those are the fitted values coming from the model, can be obtained using this equation here, where this h is a matrix. This y hat is a column of values, fitted values, and y also contain a observed y value. So that is a column. This is a column. This is a matrix. This matrix is called the hat matrix. Hat matrix because we obtain the hat values. Hat values are the fitted values, right? So this hat matrix, uh, from this hat matrix, we obtain here the diagonal values, right? So this is H matrix A. these diagonal values, H11 value, H22 value, H33 value, and so on, these diagonal values are called hat values. And those are called the leverage values also. Right. Those are important because those are used to check whether there are influential observations. If there are large hat values, then theoretically we can show that observations corresponding to those large hat values may have a high influence on the fitted model. Right. So therefore, that is one useful quantity called leverage values. And in addition to that, there is another quantity that we calculate to identify influential observations that is called Cook's distance. Right? These have some complex formulas. Therefore, I'm not going to talk about complex formulas, but it's better to know what these things are, briefly at least. Right? Cook's distance also used to identify influential observations. So Cook's distance for the observations can be obtained. For each observation, there's a leverage value. That means for each experiment in our data set, there is a leverage value and also Cook's distance. This Cook's distance can be obtained using the command Cook's distance and then within bracket the name of the output of our regression model. And then once I have obtained these things, earlier I had only the original data. Now I combine these quantities into the original data frame. That is just, I want to keep them, but otherwise these are enough to calculate like this, right? And then we will try to identify influential observations as well as outliers if there are outliers, right? So potential outliers are the ones that usually considered as outliers whose absolute value is greater than 2, right? Because we are assuming that the errors are normally distributed and therefore we also expect residuals to be approximately normally distributed. So we know for a normally distributed standard normally distributed because we are considering standard residuals, standardized residuals. Standardized residuals are approximately, at least expected to be approximately normally distributed. Standard norm, right? So therefore, for a standard normal random variable, about 95% of the observations are within +2 and -2. So therefore, only 5% of the observations we expect to be larger than 2 if the residuals are actually normally distributed, standard normally distributed, right? So just to check whether uh, it is reasonable to assume that the standardized residuals are standard normal, we use this criteria, right? So that is the way that we define potential outliers. So in order to identify which observations, if any, which observations are potential outliers, I use the command. I first of all put if there are any values, I will be putting those into the potential outliers name. And this is the command, which observations, which of observations with standard residuals greater than 2, which observations have student residual standard. In this case, I'm actually calculating student. That is the best thing. Student residuals greater than 2, right? So from that, I will, if there is any observation whose studentized residuals greater than 2, that those observation numbers will be in potential outliers. I will show you in the next part if there are any such observations. And then I find out influential observations. Again, potentially influential, not really influential necessarily. Here, I'm going to identify some potentially influential observations. The criteria for that is Cook's distance greater than 4 divided by n, where n is the number of observations we have. N is the number of rows in the wire bonding data set. So that is the same as number of observations, right? So that is the criteria. if the Cook's distance is greater than 4 over n, for some observations, those observations are considered as potentially influential observation. Right? So those observations, if any, will be now uh, stored in this name, influential observations. And in addition to that, as I mentioned, high leverage values also indicate possible influential observations. So therefore, I uh, store, if there is any observations with high leverage observation, I will be storing them under this name, high leverage observations. How do we decide whether it is high or not? This is the usual criteria used, right? If a leverage value is greater than 2 times P over N, where P is the number of parameters in the model, right? Length of the coefficients in the fitted model, right? So that is how you define the P here, right? So if a leverage value is greater than 2P over N, that kind of values are considered as high leverage values. So I find out if there is any, which observations have high leverage values, right? So after I give this command, I ask the computer to print, right? Print the potential outliers. So the potential outliers as observations whose absolute studentized residuals are greater than 2, there are 3 observations. 8th observation, 12th observation, and 29th observation have studentized residuals which are greater than 2 in absolute value. So that means greater than positive 2 or less than negative 2. And influential observations, according to this criteria, there are 2 influential observations, 8 and 12. So you can see that 8 and 12 may be also potential outliers. And 29 is also potential outlier according to this criteria, right? And then high leverage values, there are 2 observations whose leverage values are considered as high according to this criteria, 19th observation and 20th observation. Right. So actually at this point, I have only the data. I cannot go back and see whether there has been any error in recording or some other kind of mistakes have been uh, happened when collecting data. But in real practice, if you are collecting data, if you have collected data, once you have identified these observations, you should usually go back and check whether there are any errors. Right? If there are errors, for example, recording errors or some other kind of errors, if it is possible for you to correct them, then you should correct them and then refit the model with those corrected observations. Right? And otherwise, if, for example, if there is a very large data set, if you have a very large data set, and even if you are not able to find out an error, but if you think there may be some unusual observations, you might want to remove them. If you have large enough observations, several observations at the same experimental level, right? For example, this 18 and 12. For example, let's look at 18 and 12. 8 and 12, right? 8 and 12. We had 8 and 12, yes. So eighth observation came with force 40, power 90, and temperature this one. 12 is something else. So with this experimental level, actually I have only one observation, right? For example, if I had several observations with the same experimental conditions, 40, 90, 2 to 515, then when some observation is extreme, it's very easy to identify. And it may be, if you don't know what the actual observation is after finding out your records, you may safely remove that observation because you already have more than one observation, right? If you have 2 or 3 observations at least at the same experimental level, you could have easily removed that possibly erroneous observation if you cannot correct it. So therefore, when you are carrying out this regression, residual analysis, and when you are finding this kind of unusual or influential observations, you should not automatically remove them. You have to think carefully to whether to remove them or not. Right? Sometimes, even though according to these criteria, it's shown as an outlying observation. You may need to keep that. Even if it is shown as an influential observation, you may want to keep that. Otherwise, the model may not be practically applicable because you may have removed some practically correct observations. So in that case, what you have to do is you have to go for some other model, right? Change the model to fit those observations also, rather than removing some observations and then keeping with the final fitted model, right? So therefore, you have to be careful in fitting models. Right. So at this point, actually, I cannot do anything because I don't have any information about the original data. So anyway, this is an important step when you are carrying out a regression analysis. And then what I have done is I have now plotted some graphs to check whether the model assumptions regarding the errors are reasonable. Remember, again, I check whether these model assumptions using residuals, not using errors. Right. So one important thing to look at is uh, the scatter plot of residuals versus the fitted values. In multiple linear regression, this is an important graph. Right. So in this case, standardized residuals or studentized residuals are the ones that you should consider. As I mentioned, studentized residuals are the best ones to consider. But here I have looked at standardized residuals because that is the one that you will usually see in a lot of books and research papers. As I mentioned, in most of the cases, standardized residuals and studentized residuals are roughly the same. Right. So what do we look at? What do we expect this graph to look like if the model assumptions are reasonable? What model assumptions can we check using this graph? Well, we can check several assumptions using the same graph. One model assumption is that the fitted model is a reasonable model, right? That means it contains all the important variables, right? If it doesn't contain all the important variables, there may be some other pattern when uh, you will see some kind of pattern when you draw this scatter plot, right? So, but if the fitted model is a reasonable model, then you will not see a pattern. Right. So in this case, you don't see a particular pattern. What you expect is actually this residual plot, the residuals to be roughly between -2 and +2, around zero, roughly symmetric around zero. That means roughly half of the residuals to be above zero and roughly half of the residuals to be below zero, for example, without any particular pattern. Right. We can check the model assumption that is called the homoscedasticity assumption also using the same graph. Right. That is, we are assuming that the variability of errors is the same for all the x values, right? And here we expect a randomly scattered residual plot if the homoscedasticity assumption is reasonable. So according to this graph, again, we say homoscedasticity assumption is reasonable. Right? And then usually it is important to plot the residuals, standardized residuals versus each x variable in the model. Now here in our model, two variables are in the model, power and uh, the other one, yeah, I have got this wrong actually. One is the power, the other one is temperature, right? So usually we have to plot standardized residuals versus power and also standardized residuals versus the temperature, right? Uh, and there also we expect residuals to be randomly scattered around zero and almost all the residuals to be between -2 and +2, right? Only we expect outliers to be uh, above +2 or below +2. And also we expect no pattern, right? For example, if we see some kind of like the residuals are within a funnel shape or triangle shape, increasing variability, that indicates that the variability of the residuals are increasing with that variable. And that is not a good sign. That is an indication of a violation of the homoscedasticity assumption, right? So in that case, you will have to do some remedial take some remedial measures to correct that problem. There are several methods that you can apply, of course, but I cannot explain those things in this short video. But in that case, you have to be careful. You have to take a remedial measure, right? And by a mistake, I have, instead of plotting it versus temperature, I have again plotted versus power. This should have been temperature here. And actually, I have seen that graph. In that graph also, there was no pattern, right? So therefore, the residual plots against the fitted values, power and temperature actually do not exhibit any strong systematic pattern. Therefore, there is no serious evidence of model inadequacy, right? There's no and also the spread of the residuals appear to be reasonably constant across the ranges of the fitted values and the explanatory variables. Hence, there is no serious evidence against the assumption of homoscedasticity. But there are few which we already have seen that identified few observations which might be outliers and possible influential observations. Those are actually these two observations. You can see that this observation and this observation is less than -2, but it's very close to -2. Therefore, according to this graph, I think we don't have to worry too much because anyway, we expect about 5% of such residuals to be outside that band. No? Right? So here only two, right? We have 30 observations out of those two, and one is almost two. It's not very much different from -2. Only one observation in therefore can consider as at least somewhat different from two, -2. But that's again very, very minor. The departure is only very minor, and therefore we are not going to worry too much about it at the moment. And of course, you have to go back and check your data, records, and so on. If there is an error, you may be able to correct it. But for the moment, for this analysis, I'm going to just keep it. Right. And then, in addition to that, in order to identify influential observations, we have already identified the influential observations. Those were also 8 and 12. And if I look at the graph here, I have drawn the Cook's distance versus the observation number, and it shows that there are two observations which have Cook's distance greater than the cutoff value here. The cutoff value was 4 divided by n, right? So that cutoff value, right? So these two observations, observation number 8 and observation number 12. And as I mentioned, we are not going to deal too much about them, even though they are somewhat, they may be influential. And then I have looked at some graphical method to check whether the errors are normally distributed. Of course, in this case, we are checking whether the residuals are normally distributed. Because if the errors were normally distributed, then the residuals should be normally distributed, especially studentized or standardized residuals should have a standard normal distribution. So this is the graph, something, the graphical method called QQ plot, normal QQ plot, where, remember this, as I mentioned in some other video, some people interpret this as the regression model. No, this is not a regression model. In this case, actually, what you're looking at is not a regression line, because in our model, there are two variables, X variables. So what we are really having is a response surface than a response line, right? So this is not the regression line. This is just y equal to x line. For example, this is the sample quantiles of a normal distribution of our data. On this axis, theoretical quantiles of a normal distribution. So what we have plotted here is, or what our plots here is sample quantiles versus the theoretical quantiles. Uh, so if the assumption of normality is correct, then the sample quantile should be approximately equal to the theoretical quantiles. So therefore, if I draw usually the line with a straight line with slope 45 degrees angle, then the point should be close to that line. Right. So remember, this is not a regression line. This is just a reference line to see whether normality assumption is reasonable. Right. If the normality assumption of errors is reasonable, then residuals should be normally distributed, and therefore standardized residual should be standard normal. Right. So therefore, when we look at the sample quantiles of us coming from the observations and the theoretical quantiles of a standard normal distribution, they should be approximately the same. Right. So just to see whether they are approximately the same, we have drawn the reference line here with slope equal to 45 degrees. Right. So this is not a regression line. This is just reference line to check whether the normality assumption is reasonable. In addition to this graphical method, we can also carry out a formal normality test, right? So here I have carried out something called Shapiro-Wilk test. It's called Shapiro test in R. And in that test, the null hypothesis is that residuals are normally distributed. That is the null hypothesis. And the alternative hypothesis is that residuals are not normally distributed. So we make the decision based on the p-value. In this case, the p-value is greater than 0.05. Therefore, we do not reject H0. That means we accept the H0. That means we decide that the residuals are normally distributed. So that assumption, therefore, normality assumption is okay. The Cook's distance plot indicates that a few observations may be influential, but we have already decided not to worry about that, and we cannot do anything at this point. Actually, we don't know any information about the data, but you have to be careful when you are interpreting the results. The normal QQ plot supports the assumption that the residuals are approximately normally distributed. In addition, Shapiro-Wilk test also gives the p-value. Therefore, there is no evidence against the normality assumption. So therefore, overall, right, we can say the residual analysis suggests that the reduced model is reasonably acceptable. The regression model assumptions appear to be reasonably satisfied. Overall, the reduced model is statistically significant and explains a reasonable proportion of the variation in strength. Right? It was more than 60%. However, nearly 66%. However, the possible outliers and influential observations should be investigated carefully before drawing final conclusion. Right? So as I mentioned, if there are errors, you can correct them and refit the model, right? Otherwise, if there are very, very strong influential observations or outliers, and if they are real observations, this model may not be suitable. So we'll have to try some other model that will fit with those observations. Right. But here we don't have that bigger problem. Therefore, I'm going to just consider them as usual correct observations. So finally, the fitted model that we are going to consider is this model y hat. That is the uh, fitted strength values is given by this value plus this times power plus this times temperature, right? So these are coming from this output here, right? So this is the estimated constant term. This is the estimated parameter comes with the power. This is the estimated parameter comes with the temperature. So therefore, we can interpret, for example, the effect of these variables, right? So if the power, if the temperature, if we keep temperature at a fixed level, right, some level, and if we increase the power by 1 unit, then according to this model, uh, Y, that is the strength, will increase by 0.4983 units on average, right? On average, right? That means if you keep the temperature at some fixed level, and if you carry out several experiments with uh, some power and then 1 unit more than that, right? So the difference in the strength under those two conditions with a given power value and power plus 1 unit. So if you carry out several experiments, then on average, the difference between the strength will be this amount, right? So that according to this, so generally we say if the power, if keeping temperature fixed, if power is increased by 1 unit, then the strength will increase positive value. Therefore, it's increased by 0.4983 units on average. On average is important, right? And similarly, if you keep the power level at a fixed level and if you increase the temperature by 1 unit according to the unit used in this experiment, right? And then the strength will increase by 0.1297 units again on average. So that's how you can interpret the effect of these two variables, right? Keeping one fixed, if you increase the other one's power, then the amount of increase or decrease will be represented by the coefficient. If the coefficient is positive, then on average, y will be increasing. If the coefficient is negative, then on average, y will be decreasing. Right. So based on the fitted regression model, power and temperature have statistically significant positive effects on ball bond shear strength. Thus, an increase in either power or temperature is associated with an increase in the expected strength when the other variable is held constant. Right. Force and time do not have statistically significant effects after accounting for power and temperature. Right. Actually, there was something missing that I forgot to tell you. After you fit the model in the residual analysis, another thing that you should usually do is fit the residuals, plot the residuals versus the variables that were excluded from the model also. That is a good thing to do sometimes to see whether there is any, at least some kind of pattern uh, remaining in the residuals in terms of that variable. For example, when you plot the residual versus uh, one of these variables that we, for example, force, if there is some, at least a weak positive linear relationship, for example, then you might include that variable into the model and then see whether the coefficient will be significant or not. Most of the times it may not be significant, but that's a good practice also. In addition to plotting the residuals versus the variables that are already in the model, it's also a good thing to plot the residuals versus the variables that are not included in the model to see whether there is any remaining pattern that we can use to improve the model. Right. So that is something that I forgot to mention earlier. So therefore, the residues model identifies power and temperature as the main predictors of the ball bond shear strength. So that is very basic. That is a very basic example of a multiple linear regression model uh, used to identify the effect, right, of variables, right? Here, four variables were used, but finally we have found out that uh, the only two of the effects are significant, right? We can accurately predict to certain level. 66% of the variability can be explained. Variability in the strength can be explained using just two variables. Even if you use all four variables, the same, almost same amount of variability only can be explained. Therefore, there's no point of having four variables, right, in the model. It's enough to have two variables in the model. So that will conclude this example on the multiple linear regression. I will do one more video explaining the response surface method, because that is also some method that I have seen used in research papers. It's particularly in engineering research papers. So that will be included in the next video.